The composition of two functions, g and f, is the function we get from doing f first and then g. So if we let f of x be given by f of x equals x squared, and we let g of x be x plus 3, then g, f of x, is given by, well, we do f of x first, and that's x squared, and then we apply g to the whole of that. Now, since g just adds 3 onto a number, g of x squared is x squared plus 3. So g f of x is x squared plus 3. Here's another example. This time we'll let f of x be given by f of x equals 2x, and we'll have g of x being e to the x. Now, to get g f of x, again, we write down what f of x is. That was 2x. And then we apply g to the whole of that. Now, g of x is e to the x, so g of 2x is e to the 2x. So again, we have here g f of x is e to the 2x. Sometimes the composition of two functions is called the function of a function. And here's another way of writing it down. We sometimes write g f of x as g, little circle, f of x. Now, you don't have to use this notation yourself, but you might see it in classes or in workbooks, so it's important to know what it means. The order in which we compose functions can make a big difference. If you remember our first example, we had f of x being x squared and g of x being x plus 3. We'll see what happens when we do g first and then f. So this is f g of x. So this time we write down what g of x is first, which is x plus 3. Then we apply f to the whole of that. Now, applying f to something just makes it square. So f of x plus 3 is x plus 3 all squared. And that's x squared plus 6x plus 9. And if you remember, g f of x was just x squared plus 3. So you can see here that changing the order in which we compose these functions makes a big difference. Now we've looked at how to compose functions, we'll look at how to decompose functions. If I have a function like h of x equals e to the 2x, we've already seen that we can write h as a composition of two functions. H of x was equal to g f of x, where f of x was 2x, and g of x was e to the x. Let's decompose another function. This time we'll have function h of x equals the cube root of 2x plus 1. Now, first here we send x to 2x plus 1, and then we cube root the whole thing. So if we let f of x be 2x plus 1, then h of x is the cube root of f of x. So then if we set g of x to be cube root x, we get that h of x is g of f of x, so that's g f of x. Being able to decompose functions will be very important when you come to do things like integration and differentiation. Now there are some pairs of functions that can't be composed. Let's have f of x being minus x squared, and we'll have g of x being natural log of x. Now f of x is less than or equal to 0, whichever x you pick. But g of x is only defined if x is greater than 0. So g of f of x doesn't exist. There are also some pairs of functions that can be composed for some x, but not for other x. This time we'll have f of x equals 4x minus 6, and we'll have g of x being square root of x. Now, g of x is only defined if x is greater than or equal to 0. So gf of x can only be defined if f of x is greater than or equal to 0. And f of x is greater than or equal to 0 only if x is greater than or equal to 3 over 2. So gf of x is only defined for x greater than or equal to 3 over 2. The values of x for which gf is defined is called the domain of gf. The range of a function is the set of all the values a function can take. So for example, if f of x was e to the x, the range is given by f of x is greater than 0, because e to the x can only be greater than 0. Similarly, if we have f of x being, say, sine x, then the range is f of x is between plus 1 and minus 1. The range of a composite function must lie within the range of the second function we apply. Here's an example to show you this. We'll put down f of x equals x minus 8 and g of x equals x squared. Now for f of x, the range is, well, f of x can take any value. But for g of x, the range is g of x is greater than or equal to 0. Now let's look at the range of the composed function gf. G f of x is, well, f of x is x minus 8, and g of x squares it, so gf of x is x minus 8 squared, which is x squared minus 16x plus 64. But since gf of x is something squared, and all square numbers are greater than or equal to 0, gf of x is greater than or equal to 0. So the range here is gf of x is greater than or equal to 0. So you can see here that the range of gf is the range of g. Now let's look at what happens when we compose them the other way round. So this time fg of x. Well, again, g of x is x squared, and applying f to the whole of that gives us x squared minus 8. Now since g of x is greater than or equal to 0, and here we're taking away 8, this whole thing must be greater than or equal to minus 8. So the range is fg(x) is greater than or equal to minus 8. Now, fg of x's range isn't the same as f of x's range, but it's certainly contained in the range of f of x. So these two examples show you that if you're given a composed function, the range must lie within the range of the second function you apply, but doesn't have to be all of it.